So we're going to have a bit of a look at column chromatography, which is, I guess, a more general sort of category of chromatography than paper or thin layout chromatography. So under the heading of column chromatography, there are a few different types of chromatographic sort of systems and processes that we can look at. However, first of all, we're just going to look at the general idea of column chromatography and what this means, and sort of the general criteria for a process to be referred to as column chromatography. So, in column chromatography, we have what's called a column. So this column here is kind of like a burette that we might have used in volumetric analysis. So it's kind of a vertical glass tube containing, lots and lots of stuff. Now, what it contains is these solid particles here, all these little tiny solid particles filling up the column, and they are the stationary phase. So they are small solid particles, and basically what they do is they fill the column, and they are what we pass our sample through. So they're small solid particles. Now the mobile phase, when we're talking about just general sort of column chromatography like this in its simplest form, is just any sort of solvent that we drip into the top of the column and pass through the stationary phase. So the mobile phase comes from up here. It's just sort of, whatever solvent we may be using on a particular occasion. And what we do in column chromatography is, we drip some solvent through the column just to get things going, and then we put our sample, we just sit it on top of the stationary phase inside the column. We just kind of put it in the top of the column, sitting on top. What happens is the mobile phase, it keeps dripping on top of the sample, slowly dissolves the sample, and carries the sample through the column. And obviously the different components in the sample are going to take different amounts of time to pass through the column and escape, depending on how they adsorb onto these small solid particles of the stationary phase and desorb back into the mobile phase. So what happens is, the components separate as they move through the column due to that adsorption and desorption. And then when things come out the bottom, the stuff comes out the bottom, this kind of mixture of mobile phase, or the solvent, and the components from this sample, we call the stuff coming out the bottom the eluent. Now this is kind of, this is no one specific substance. As I said, it's a mixture of these components in the sample and of the mobile phase that we're using. And so what happens is, in order to form the chromatogram and analyze how long different components in the sample are taking to come out, we basically pass the eluent through a detector. So we might have a detector here, for example, a UV detector is one that's commonly used. And so basically in a UV detector, some UV light is shone through the eluent stream onto a detector here. And depending on what sort of substance is in the eluent at a given time, different amounts of UV are going to pass through. So different substances, maybe components of the sample or the mobile phase, are going to absorb different amounts of UV light. And thus, as the eluent, as the makeup of the eluent changes, as different components from the sample come out the bottom of the column, different amounts of UV light are going to be allowed to reach the detector, and so we're going to get, some varying readings, which we'll be able to analyze a little bit later on. So this is sort of the broader idea of column chromatography, and there's one more factor that it's important to be aware of, and that is the idea of retention time. So we know we have a retardation factor when we're talking about paper or thin layer chromatography. Well, retention time is basically the equivalent of that when we're talking about column chromatography. So as you can imagine, retention time refers to the amount of time it takes for a given component of the sample to move through the column and exit in the eluent. Now, we consider time 0 to be when the sample is added to the top of the column and the sample is placed on top of the column. And so we measure the time between when the sample is placed on top of the column and when it leaves the bottom. And that difference, the length of time that takes, is called the retention time. And so, like the retardation factor, the retention time for a given sort of component or substance will be constant if we repeat the process under the same conditions. So if we use the same column with the same amount of stationary phase and type, same mobile phase, same everything, and we put the same sort of component in the top of the column, it will have the same retention time. It will take the same amount of time to get out the bottom of the column. So this is sort of a general outline of the ideas surrounding column chromatography. And so what we're going to do now is have a look at the two more specific categories of column chromatography. So the first kind that we'll look at is one called high performance liquid chromatography, or HPLC. Now, if I'm going to draw a diagram of HPLC, it's going to look pretty much identical to this general diagram I've drawn here of column chromatography. Basically, as you can imagine, because it's high performance, there is just a slight change. So whereas in regular column chromatography, we just deal with some small solid particles in the column, acting as the stationary phase, in high performance liquid chromatography, the stationary phase is basically made up of much smaller particles. So the stationary phase is very small particles. And so what this does is basically if we have much smaller particles and we still fill the column, there's going to be a much greater total surface area total surface area of the particles. If we had one large particle filling the whole column or millions of small particles, there's going to be more surface area on the total. There's going to be more total surface area on the millions of small particles than there will be on the one large particle. So having lots and lots of small particles means we have greater surface area on the stationary phase, which means that there's going to be more adsorption and desorption going on of these components. Because there's more surface area, there's more surface to adsorb to. And so this adsorption-desorption cycle is going to happen much faster and much more frequently. And because of that, basically, we're going to get much better separation of the components of the sample. And so that's why we get the high performance from these small particles, make everything a bit clearer and a bit more accurate. Now, because these particles are so small and there's such high surface area, another issue that we're going to come across is it's going to take a very long time for everything to move through the column because there's so much adsorption going on. And so what we do is we often conduct high performance liquid chromatography at very high pressure. So we pump the mobile phase through at a very high pressure, and what that does is it speeds things up a bit. We're not sacrificing the extra accuracy produced by having very small particles, but we are sort of preventing the extremely long time that may result from having such small particles. So we pump the mobile phase through at high pressure when we're doing high performance liquid chromatography. Now that we know that everything happens at high pressure in this form of chromatography, it's easy to get this HPLC acronym a little bit mixed up. It's important to remember that the P here stands for performance and not pressure. So it's high performance liquid chromatography and not high pressure liquid chromatography. That's important to have that clear in your mind. So that's one type, high performance liquid chromatography. That is a form of column chromatography. Now another form of column chromatography is gas chromatography, or if we shorten that, GC. Now in gas chromatography we again have a mobile phase and a column, and sort of a detector and a retention time and all that kind of stuff. It's just sort of set up a little bit differently because we're dealing with gases. So this white coil here, this is the column in gas chromatography. So this is the column round here, and this is filled with stationary phase. And so what happens? There's two different types of gas chromatography. There is gas liquid chromatography and gas solid chromatography. And basically, the liquid or the solid in these two different types refers to what the stationary phase is. So if we've got the stationary phase here, and we look at the two different types, in gas liquid chromatography, the stationary phase is the liquid that is coating all this solid inside the column. So in gas liquid chromatography, this column is still filled with lots and lots of small solid particles. However, these small solid particles are coated in a certain type of liquid, and it's that liquid which acts as the stationary phase. So that is the stationary phase in gas liquid chromatography is this liquid coating on the small particles. In gas solid chromatography, the stationary phase is simply the solid particles that fill the column. So these are often just sort of absorbent solid particles. So this is basically, in gas solid chromatography, our stationary phase is basically just the same as it is over here. It's just these small solid particles filling the column, which in this case is a coil. And so they're the two stationary phases that we could deal with in gas chromatography. And so, as you can imagine, as it sounds, we're dealing with gas chromatography. So everything happens as a gas. So here we have a canister full of gas. Basically, in gas chromatography, our mobile phase is a gas. And so we call this mobile phase the carrier gas, because just like the solvent over here carries the sample through the column, the carrier gas will carry the sample through this coiled column in gas chromatography. So we call the mobile phase the carrier gas. And so what happens is, again, we have our red sample here, and we inject it into this red box here. And this red box is the injection port. And so how everything works is this whole region, so this injection port and the coil and the detector, which I'll explain in a minute. So this whole area that I've underlined with the orange here is often in an oven when we're dealing with gas chromatography. And so what happens is this injection port is heated to a very, very high temperature. And so when we inject the sample into the injection port, the sample is immediately vaporized and turns into a gas. So we turn it into a gas, and that way, as we let the carrier gas out of the canister and we pump the carrier gas through the injection port and into the coil, the vaporized sample, or the gaseous sample, is then going to be carried by the carrier gas. Just the same way that the sample here is dissolved in solution, this sample is vaporized, and so now we have a gaseous sample that is kind of mixed in with the carrier gas and then carried through the column. And so just the same way that components of the sample are separated here, components of the gaseous sample here are separated based on how they adsorb and desorb to the stationary phase inside the column. So it's very similar, however, basically everything's just converted to a gas by having everything at very high temperatures. So again, what we have at the end is a detector which detects any changes in the stuff that's coming out, in the eluent that's coming out of the column at the end. And by detecting changes in that substance, it can detect how the different components separate through the column. And so we've talked about how a UV detector works, and so there's another type of detector that's often used in gas chromatography, and that is a flame ionization detector, or an FID, so flame ionization detector. And so what that does is, again, this detector is also very hot, and it ionizes the gas that's coming out of the column. It ionizes the eluent as it leaves the column, and by ionizing the eluent, we know that ions can conduct electricity, and so depending on the substance leaving the column, depending on what the eluent is, it's going to be ionized to a different extent, and thus it's going to conduct different amounts of current. So basically what it does is this detector funnels some gas into an open space, ionizes that gas, and then sees how much electricity can be conducted by those newly formed ions, and that's how it detects the changes and the different substances coming out of the column. So that's not too important, but it gives you a little bit of background about how we detect changes in the substance leaving the column. So there are the two different types of detectors, and these are the two sort of major types of gas chromatography. We've got high performance liquid chromatography, which just fits the standard sort of visual mold for column chromatography with a vertical column. We drip solvent through, dissolving a sample and carrying it through this vertical column. Now, gas chromatography has the same premise. We've got a column filled with some stationary phase, and we pump solvent through the sample and carry the sample through the column. However, everything occurs as in the gaseous state. And so that's the main difference. And so those are the two main types of column chromatography. Now, in the case of each detector, each of the detectors is going to produce what's called a chromatogram. Now, a chromatogram in column chromatography is basically a graph of time and recorder response. And so we're going to go over how to analyze these chromatograms in another few videos. But just so you're aware, what's produced in these two forms of chromatography is this recorder response chart. And so as it measures the response of the recorder as the eluent passes through it, and so we might get a flatline response caused by the mobile phase, which we know that there's going to be a lot of mobile phase leaving it, so that triggers a flat response. Then every now and then we get a bit of the sample coming out the end of the column. So what that's going to trigger is a bit of a recorder response, so a bit of a spike there, and so then a flat line as mobile phase continues to leave the column, and then another spike as another component of the red sample here leaves. And so that's kind of what our chromatograms are going to look like. And we'll go over how to analyze that in another video, but that's a basic outline of how column chromatography works.